Imagine a place so dense that a sugar cube-sized amount of matter would weigh 1 billion tons. Welcome to the heart of a neutron star, the universe's ultimate mystery machine. Inside these cosmic titans lie secrets that could rewrite the very laws of physics, unlock new states of matter, and reveal what truly happens when gravity is pushed to its extreme. Are you ready to explore the mind-bending secrets hidden deep within a neutron star's core? Let's dive into the unknown and uncover the universe's most astonishing mysteries, moments of catastrophe and creation. Before delving into the depths of neutron stars, it's essential to grasp the concept of cosmic tipping points. These are moments when the universe, or a star, reaches a critical threshold, causing a dramatic transformation or catastrophe. Think of a star building up magnetic energy until it erupts in a solar flare, or a supergiant fusing iron in its core, leading to a hypernova that outshines entire galaxies. Or consider a magnetar, a neutron star with an intense magnetic field, where pressure causes surface star quakes that unleash powerful gamma-ray bursts. These phenomena exemplify the universe's delicate balance. Stability teeters on a razor's edge, and crossing a tipping point can unleash chaos or birth new structures. But remarkably, the universe often has safety nets, subatomic forces and quantum principles that prevent total destruction, maintaining cosmic order amidst chaos. Neutron stars as the ultimate physics experiments. Among these cosmic titans, neutron stars stand out as the ultimate testing grounds for physics. They are tiny dead stars, no larger than a city, yet their mass exceeds that of the Sun, compressed into a sphere just about 20 kilometers across. The gravity on their surface is so intense that mountains are mere fractions of a millimeter high, and objects falling onto them would accelerate to half the speed of light before impact. Their interiors reach densities and pressures unmatched elsewhere, putting matter under conditions akin to those mere moments after the Big Bang. Inside their cores, matter exists in states that challenge our understanding, forcing physicists to revisit and refine their theories about the fundamental nature of reality. Peering into the Sun, the first step toward understanding extreme matter. Our journey begins with our closest star, the Sun. Although it seems stable and familiar, the Sun's interior holds clues about the extreme physics at play inside neutron stars. The Sun's outer atmosphere, or corona, is a bubbling, seething layer of plasma heated to over 1 million degrees Celsius, constantly launching solar flares and coronal mass ejections. Beneath that lies the chromosphere and the photosphere, where temperatures are around 5,500 degrees Celsius, yet the material remains only partially ionized, a mixture of hot gases and plasma. To understand what's happening beneath the surface, scientists like Meghnad Saha developed the Saha ionization equation, which helps determine the degree of ionization based on temperature and pressure. This tool allows astronomers to infer the conditions inside the Sun's core, where temperatures soar to around 15.7 million degrees Celsius, and hydrogen nuclei fuse to produce helium, releasing enormous amounts of energy. The force balancing this nuclear fusion, the outward pressure of hot plasma against inward gravity, is known as hydrostatic equilibrium. This delicate balance ensures stars like our Sun remain stable for billions of years. The equation of state governs this balance by describing how matter responds to changes in temperature, pressure, and density. Although we cannot directly observe the Sun's core, neutrinos, elusive subatomic particles produced during fusion, offer a window into these hidden depths, confirming the Sun's internal conditions with remarkable precision. From sun to stellar graveyard, the end of a star's life. As stars exhaust their fuel, their fate depends on their initial mass. Small to medium stars like our Sun gradually shed their outer layers, forming planetary nebulae, leaving behind white dwarfs, ultra-dense remnants supported by quantum degeneracy pressure. White dwarfs are extraordinary objects. A sugar cube of their material would weigh as much as an elephant, owing to the degeneracy pressure arising from the Pauli exclusion principle, and quantum rule preventing identical particles from occupying the same state. More massive stars, however, face a different destiny. When their cores run out of fuel, they undergo a supernova explosion, a titanic release of energy that briefly outshines entire galaxies. The core collapses into a neutron star, a dense object composed primarily of neutrons packed so tightly that a teaspoon of its material weighs more than the combined population of all humans who have ever lived. The birth of a neutron star. The formation of a neutron star hinges on the TOV limit, the maximum mass a neutron star can support before collapsing into a black hole. This limit, initially estimated at about 1.4 times the mass of our Sun, has been revised upward over the decades thanks to advances in observations and theory. Modern estimates place it between 2.2 and 2.9 solar masses. The remarkable stability of neutron stars is rooted in neutron degeneracy pressure, a quantum mechanical effect that arises from the Pauli exclusion principle applied to neutrons. When nuclear matter is compressed beyond the limits of electron degeneracy, which supports white dwarfs, neutrons themselves fill available quantum states, creating a pressure that resists further collapse. But what exactly is happening inside a neutron star? As we peer deeper, the layers become increasingly exotic. The outer crust is a lattice of nuclei immersed in a sea of electrons. Beneath that lies the nuclear pasta, a theorized phase where protons and neutrons form shapes reminiscent of spaghetti, gnocchi, and lasagna, due to the competing effects of nuclear attraction and Coulomb repulsion. These structures could be the strongest known materials in the universe, with their properties still a subject of intense study. Quark matter, hyperons, and dark matter. The core of a neutron star is shrouded in mystery. Traditional models suggest that at the highest densities, neutrons might disintegrate into their constituent quarks, forming a quark soup. Alternatively, particles called hyperons, strange quarks bound within particles, may appear, softening the equation of state and affecting the star's maximum mass. Recent observations, such as the neutron star designated J0740+6620, have challenged existing theories. This star, with a mass of over twice that of the Sun, surprisingly has a larger radius than some models predicted. Such findings imply that the inner core might be more squishy than previously thought, or that other exotic states of matter are at play. One exciting possibility involves Bose-Einstein condensates, a state where particles act in unison as a single quantum entity. If bosons, particles with integer spin, pair up in the star's core, they could form a condensate that provides additional pressure support, preventing collapse even beyond the traditional mass limits. When the limits are exceeded, collapse into black holes. What happens if a neutron star exceeds its mass limit? The answer is collapse into a black hole, the ultimate endpoint of gravitational collapse. Once the core surpasses the TOV limit, quantum degeneracy pressures can no longer hold back gravity, and the star shrinks to a point of infinite density, the singularity, where the known laws of physics break down. Black holes are fascinating, not only because they swallow everything that comes too close, but also because they challenge our understanding of space, time, and quantum mechanics. The collision of neutron stars often produces gravitational waves, ripples in space-time, detected by observatories like LIGO and Virgo. The quest for a theory of quantum gravity. One of the most profound challenges in modern physics is reconciling general relativity, which describes gravity on large scales, with quantum mechanics governing the subatomic world. Neutron stars, particularly their cores, are the perfect proving ground for this quest. They sit at the intersection of these theories, where the effects of both are essential. Recent discoveries, such as the 2024 observation of unexpectedly cold neutron stars, have already begun to rule out certain models of quantum gravity and the equation of state. The precise measurement of neutron star masses and radii, combined with gravitational wave data, is gradually peeling back the layers of mystery, bringing us closer to a unified theory. The future of neutron star research. As technology advances, our understanding of neutron stars will deepen. Instruments like the Neutron Star Interior Composition Explorer on the International Space Station are providing unprecedented insights into their internal structure. Despite setbacks, such as damage to NASA's delicate instruments, scientists are persevering, driven by the promise of unlocking the secrets hidden in these cosmic dens. The universe's most extreme laboratories. Neutron stars stand as the universe's most extreme laboratories, condensed matter pushed to the brink, where quantum mechanics and general relativity collide. Every discovery, from their maximum mass to their internal composition, challenges our understanding and opens new avenues of inquiry. Ultimately, exploring their secrets may lead us to answer some of the most profound questions about the nature of matter, energy, space, and time itself. The journey into their cores is far from over, but each step takes us closer to unlocking the deepest mysteries of the cosmos.